Okay. So I'm going to share my screen first, and I'm going to actually start. That will be this one, yes. Okay, so you see my schedule, and here normally you see my slides. Starting from the beginning to be better. I'll try to keep the chat open, but it's hard to follow meanwhile. So just a few words for those who did not have distance classes with me last year. What I'm used to do, but I'm open to any suggestion. What I'm used to do is that I share my slide with you, and I write directly on my slides the important thing that I want you to retain, to keep in mind. Okay. I'm also in parallel working on editing a Polycop. I would say that, yeah, a notebook of what I'm going to speak about. But it's not available now. And even if it was available, I think I will give you only after all the courses, just to be sure that you have some interest to stay connected to the Zoom class. Okay. Do not hesitate to interrupt me at any time, either because you have not understood my English, which is likely possible, or because you are missing some points and you really need deeper explanations. Okay. So for what I remember, but I haven't checked, I have to say, there are 7 slots of 1 hour 45 minutes in the scope of this course. 7 slots on which we are going to discuss of optoelectronic components, almost not system, except a little bit at the end, so mostly components, and in the frame of high-speed application, meaning gigahertz type application. Okay, so my slides are not accurate too much because you are not anymore circuit intégré and micron, so I need to update that. I think I did it somewhere. No, but yes. What are we going to discuss about? Well, there will be an introduction, so like very soon. Then we are going to do some reminders, des rappels, over optical fiber. There's someone with microphone on. Can you please? Yeah. Yeah, thank you. I think it's okay. So reminders on optical fiber, because you are going to understand very fast that optical fiber is going to be a secondary components in everything that I'm going to say. It's not an optoelectronic component, and it's a pure optical component, so it's not in the frame of what we are going to say. Nevertheless, we have to keep in mind some of the specification that we encounter in the optical fiber. Then we are going to spend like 50% of the time minimum on the laser diode, because it's clearly the most complicated component when it comes to high frequencies. And we are going to go back and deeper than what we have done last year into photo detection at high frequencies. Okay. There's something that we are going to discuss both in the laser and in the photo detection. It's the noise, something that I haven't told to you at all on the emission side. So last year I gave you some information and some notes on the noise on the detection side. But we are going to see that, especially in the context of this class, the noise of the laser is not at all a neglectable aspect. Okay. And if we have more time, because I'm a bit into, I don't know, I've never done this class at distance, so I'm not sure it's going to fit into the 7 slots. We are going to discuss about electro-optical modulators and their application. The problem being that the application of electro-optical modulators can be extremely wide. So probably I will have to reduce the scope of what I'm going to say. Okay. As you are going to see from time to time, there are some exercises. But the remark that I have most of the time from the students is that this course is very like I'm speaking a lot, and you don't. It's not very based on. It's more a course than a tutorial. Okay, so don't be surprised by that. What I speaking about the exam, it's very close to what I'm doing here. Okay, so let me just talk about the frame of the of this course. The first thing is that we are going to talk about high frequencies in short distances communication. Okay. So why do I limit myself to short distances communication? Because actually there's a strong difference between what is done for transoceanic or transnational optical communication and what you maybe as an electrical engineer you will have to deal with in your career if you are making communication by optical systems. Okay, so one very good example of that is the IEEE 10 gigabits per second, bits, not gigabytes, gigabits per second, Ethernet protocol. Okay, when you study the possibility of transmitting 10 gigabit per second with copper cables, you will come rapidly to the conclusion that it's limited to a few centimeters, in best cases 1 or 2 meters. But the problem is that in some application, you may need longer communication. So the frame of this course has come after in an internship of a student that was in the third year of the engineering program here at NSET, had an internship where he had to transmit the data from a video from a camera, so a high resolution camera, over a 10 gigabits Ethernet protocol, and the camera was set on the back of a plane, while the computer, which was dealing with the images, was in the front of the plane. And the distance was only 20 to 30 meters because it was a military plane, but it was impossible to do that with an Ethernet cable. So what we are going to discuss about is just the systems and the protocols for the optoelectronic system to deal with distances of few meters to 100 meters, and for just one signal, so not a lot of modulated signals, but at very high speed, typically 10 gigabits per second. Okay, so in what's going to happen is what we are going to see. So in short distance, what you need to retain, that in short distance, sorry, the impact of the fiber itself is almost neglectable. Okay, and the difficulty lies only in the laser and photodetector behavior. Okay, because first we want to be sure that we are capable to modulate the laser at the good frequency, and second, we want to be sure that the photodetector is capable to amplify the photodetected signal in the good frequency range. Okay, so this is the frame of this course, and we are going to see that there are plenty of things to discuss in this frame. Let's start first to deal with the optical fiber, and let's remind you what you need to know absolutely about the optical fiber. So the first thing, you remember that an optical fiber, it's a long spaghetti made in glass. Okay, so it is transparent. And you need to remember that there are two types of fibers. First, the multi-mode fibers, and second, the single mode fibers. So these two differences are very important. You remember I told you last year that in the case of multi-mode fiber, it's not exactly that there are several passes in the fiber, but that there are several solutions to the propagation wave. If you remember well, you see this figure on the right side of the slide. These are the spatial distribution of energy in the different modes that propagate inside the fiber. So it's really electromagnetic type of modes. You remember it's a linearly polarized mode that are a combination of transverse electric and transverse magnetic modes. Okay, and of course you have the single mode fibers. If you remember correctly, what I say last year is that there will be a strong impact on the there will be a strong impact on the bandwidth of the optical fiber. I'm going to do it like that. So, sorry, I'm going to erase all that. Complicated. Okay, so text here. Okay, so in case of multi-mode fibers, okay, there is an impact on the, maybe it's too small, the fiber bandwidth that is due to the dispersion of the propagation time of each mode that propagates. A lot of propagates. Okay, so basically you have several modes and they take a different time to propagate, and this will lead to modal dispersion. Okay, it is called modal dispersion. Okay, the modal dispersion, it's something that it's completely problematic, but we know that if we go to the single mode fiber, we can get completely rid of that. You just have to remember that this dispersion can be computed, okay, and it will give a delay in time, of a dispersion in time that is proportional to a term of dispersion, of modal dispersion, dm, and the length of the optical fiber. Okay, that's what we need to know about that. Okay, the second thing that we need to remind is that even in the single mode fibers, the bandwidth is limited by a second effect that is called the chromatic dispersion. I don't know why I start by even. And multi-mode fibers, sorry. So the chromatic dispersion, and this term of chromatic dispersion, it's a bit more complex than just the modal dispersion because it's related to the spectral width. Okay, so let me write the equation. And if you have a question, do not hesitate.
I do have a question about that first one. The sigma underscore delta t, that's the time, right?
Yeah, absolutely. That's the time.
Okay, the time from one mode to the other one.
Yeah, that's the dispersion. Maybe okay. I called that only delta t last year. But here I keep the sigma because it's a statistical value.
Okay.
Okay. Okay. So this time the chromatic dispersion, you see a term d lambda, that is the chromatic dispersion term, and you have. So this one I'm sure I'll change. Okay, I'm going to change that because otherwise you won't understand. So I call that delta lambda. Okay. So you have the term d lambda, that is the chromatic dispersion term, and you have the term delta lambda, that is the spectral width of the light source. Okay, let me specify that. I'm going fast because normally you know all of that. Delta lambda is the spectral width of the light source. Okay. And d lambda is, of course, the chromatic dispersion term. You remember that in the multimode fiber, you have both terms, and you have we have to do a quadratic sum to calculate that. Okay. Hold on. You also remember that the bandwidth of the fiber is computed as let me write that. Yes, here. Up. Based on this calculation, okay, you remember maybe that this is due to the analogy to a low pass first order filter, okay, where sigma delta t is either just the chromatic dispersion, either a combination of both the modal and the chromatic dispersion. So I realize here that I have any index, so I'm going to do that right now. If I can, I'm not sure. I'm going to do that like that. So modal, chromatic, and here, let's say total. Okay, and if I want to go a bit further, first I'm gonna put that in. Okay, so this term here, okay, it's square root of sigma delta t. I guess it should be an underscore probably. Okay, square plus the same for chromatic. Okay. still going fast because we've seen all that. Maybe I've changed the notation of the time. Probably I removed the sigma but last year, but it's exactly the same. Okay. What we need to know about the chromatic dispersion. So the modal dispersion is something that is purely related to the size of the fiber. Okay. The chromatic dispersion, in turn, it's important to understand that chromatic. Oh, I have everything here. Nevertheless, never mind. The chromatic dispersion, it's important to remember that it is due both to the spectral width of the fiber, the laser in our case, but also to its central wavelength. Because you remember that the term of chromatic dispersion can be either positive or negative depending on the central wavelength of the laser. And it can be either very low if you are in the micrometer range. It should be theoretically 0 at 1.3 micrometer. And it's very low above, but it's extremely high below. Okay, so let's just write this consideration. The chromatic dispersion term is depending, or depends on, the spectral width of the laser source, but also actually no, the term, no, not on the spectral width. That's the time, the dispersion time that depends on the, sorry, depends on the central wavelength of the laser source. Okay. And it's very important term at the lower frequency. Okay, it's a very important term at the lower frequency. So when we are going to design the laser, we need to think about that, and we need to understand that we are going to play with laser that are preferentially at 1 micron something in terms of wavelength, rather than 800 something or lower if we have to. Okay. So this is for the pure bandwidth aspect. The second aspect that we need to remember is the attenuation. Okay, so normally you remember this curve that is one of the most important that can be drawn for the optical fiber. That's the attenuation curve inside the silica. And this curve says that basically, if you want to have a low attenuation, you need to work at 1.55 micrometer or 1.3 micrometer, where you have very low level of attenuation. And if you know a bit of the history, you know that there is one wavelength here at 850 nanometer that is interesting because it's in history, meaning in the 70s, it was the best option in silica. So normally you remember all that. The attenuation that you need to consider is 3.5 or 3 at 850, 0.4 or 0.2 dB per kilometer at the other wavelength, and the power at the output is computed by this relationship where P out and P injected are computed in dBm, while the length here is in kilometers, since the attenuation A is in dB per kilometer. Okay, and this is pretty much everything we need to know about the optical fiber. And just to be sure that all this is well understood and well known, I will give you a short exercise. Okay, so let's make a new slide. Okay, just to be sure that you know all that, and then with the result that you're going to get, we are going to continue the discussion. Okay, so we want to make a 10 gigabit Ethernet link. Okay, with first, I already have that, laser at 850 nanometer. And second, with a laser at 1550 nanometer. With, for both cases, like that. For both lasers, we will have delta lambda that is equal to 2 nanometers. So not very good lasers. Oh, sorry, my mistake. It's not the same. Oh, yeah, it would be too easy with the same. Here, lambda 850 nanometers, and I'm going to do it like that. Delta lambda. Why not the other one? Where's delta? Delta lambda here, that is equal to 2 nanometer, while it's only 0.1 nanometers in the second case. Okay. So there's one unique question to this problem. What will be the maximum distance in both cases? Okay, considering that 10 gigabits Ethernet mean that we need to modulate at 10 gigahertz. Okay, we consider that we are doing some Manchester coding or something like that. Okay. So I propose that I give you 10 minutes to recall to all your memories and try to give me the actual value of the maximum distance in both cases. We are going to consider only, of course, considering only the bandwidth issue. We are not going to discuss about the power issue. Okay, we're not discussing this. Okay, so I leave this here. You have, allez, let's say 10 minutes, and you are authorized to ask question, of course, if you don't know how to tackle this problem. Okay. I did not specify it, but we are using a single mode laser, single mode fiber. I hope everyone is trying to solve the problem. I have to believe that. At the end of the 10 minutes, I'm going to ask someone to share his screen to show us the result. What's the dispersion term? Okay. Well, you can use this curve. Well, okay, now I'm going to give you a value. Here, d lambda, d lambda equals 80 picoseconds per nanometer per kilometer. Okay, so actually minus 80, because you see that on the curve it's negative bit of the curve. And here we are going to take plus 10. Do you need me to show you this back? Actually, maybe this would be better. Or even this. So I think you have enough time. Huh? I think it was not that complicated, considering that we took only a single mode fiber. Okay. So let's discuss that very briefly. And we just recall this relationship here. Okay. So in the first case, the sigma delta T lambda will be equal to 2 in nanometer times 80, because actually it's not in the relationship, but you shall remember that there's no negative delay. 2 times 80 times the length of the optical fiber. This hasn't changed. Okay. Okay, since the bandwidth, I'm going to use this relationship here, is here. Okay, then actually, I'm going to take that here, region B. Then the bandwidth, the length of the optical fiber, maximum. Let's do it like that. So here, that will be equal to 0.35 divided by 160 times 10 10 gigahertz. No, but this is time 10 minus 12, because this is in picoseconds. Okay, the time times the bandwidth, that will be 10 gigahertz, so 10 power of 10. Okay, I'm not sure you have it properly. Like that would be maybe better. So eventually that's 0.45 divided by 1.6 in kilometers. Okay, so I don't know what it makes. If someone has the answer, you're welcome to give it to me.
I found 219 meters.
Okay, 219 meters. So this is the worst case scenario. Okay, and then in the second case, or second option, okay, we will find roughly the same thing. Okay, apart that will be slightly different. We will find 0.1. I don't want to do the point actually. Time 10. Okay, which makes 1 picosecond. And the maximum length will be equal to 1 picosecond times 10 gigahertz. And in this case, I believe it's 3.5 kilometer. No, what should it be? So let's do 35 kilometer, right? Can someone confirm? I'm not out for a decade. Yeah, I think that's it. Okay, so 35 kilometers. So worst case scenario, 220 meters. Second case scenario, 35 meters. What is interesting here to understand is that these distances are already quite good in the sense of application of the 10 gigabit Ethernet. Okay, you will rarely exceed 200 meters in such an application. Also, what also matters to understand is that at these distances, the attenuation is ridiculous. For example, here at this distance, it's less than 1 kilometer. So if you look at this curve, the attenuation, since we are at 850 nanometer, so we have 3 dB per kilometer roughly, we have done less than 1 kilometer. So it means that the power here has been divided by less than half. Okay. Same here with the second option. So here we have 0.2 dB per kilometer. So it means that we are going to lose 7 dB. So it's roughly we have divided the power by 4, which is ridiculous. I mean, considering that if you are sending 10 milliwatts, you will still have something like 2 milliwatts at the output. So with such short distances, the power budget is not even a discussion. Okay, all laser sources that you can imagine will fit into this argument. Okay, this condition you are going to fit in this application. Okay, so that's why I wanted you to do this calculation to understand that when discussing about high-speed optical system in reasonably short distances, up to several kilometers, the fiber is transparent, and this is not a joke. Huh? It's literally you don't see it either for the bandwidth, either for the amplitude. So it means that the only concern that you have is on the pure optoelectronic components. Okay.
I have a question. I didn't understand very well how you did that calculation. So you're dividing 0.35 over.
Okay. I'm replacing here in this second equation. So the equation of the bandwidth. I'm replacing sigma delta t by this term here.
Okay.
So the maximum length is the length which still allows the bandwidth to be 10 gigahertz.
Okay.
So basically, how can I write it? Maybe I will write a complete equation. So the length maximum, that will be 0.35. I need to do fraction. Divided by d lambda times delta lambda times b. Where's my equation? Here. Okay, where b is the 10 gigahertz. Or maybe I should annotate it like b requirements. Okay. Okay. So I have no more space. I'm going. You know what? I'm going to shift that here. This here. Okay. Because of course, if I increase the length, I will have available bandwidth in the optical fiber that will decrease. Okay, so this is how I've done the calculation.
Okay, thank you.
You're welcome. Just a reminder, okay, what we need to retain on the fiber again. This is regarding the attenuation and the impact of the wavelength. That is important. And you know that behind the wavelength, what is at stake is the type of semiconductor that you are going to use. Okay, so and the kind of application, and the comparison with the copper cables, and you see that the bandwidth here 150 dB kilometer. So if you want to do 10 gigahertz, okay, you have almost to divide the length by 10. So it means that you are limited to 100 meters with an Ethernet cable or a coaxial cable. Okay, so the maximum distance that you can achieve will be, sorry, my mistake, this is the attenuation. It's 0.2 megahertz kilometer. So you have to divide by 50. I found the value be too big. You have to divide by 50 the distance to reach 10 gigahertz. So for an Ethernet cable, a standard Ethernet cable that you have at home, you are going to have only 20 meters of possible distance. And if you go to a coaxial cable, then you will be limited to you have to divide by 100. So you will have, no, my mistake. For the coaxial cable, you are limited. Yeah, you have to divide by 100. So you have only 10 meters with the coaxial cable, and you should be probably in millimeter with an Ethernet cable. Okay, but because you need to multiply by 5,000. Okay, so a 5,000 of a kilometer of the distance. Okay, so I don't know. I haven't done the calculation, but it's ridiculous. Okay, so this is what we need to remind as concerns the optical fiber. So now we are going to do still a little bit of reminders, but with the laser and especially the photoelectric effects to start with. Again, if you want to interrupt me, if I'm going too fast, you don't hesitate to do it. I'm considering that you have seen that already. So the first thing before we address the problematic of the laser diodes itself that we need to remember is that everything here is based on the photoelectric effects. I recall you what are the photoelectric effects. Remember, there are 3 of them. I will spend some time first on the emission. Spontaneous emission, I'm sorry, there's still some French remaining on my slides. So the spontaneous emission comes when you have an electron. So the dark point here is an electron that is in the conduction band. When it goes down spontaneously to the lower band, the valence band, then it will produce 1 photon. This photon has an energy h nu that is equal to the difference of energy between conduction and valence bands. Okay, so that's for the spontaneous emission. And what is important in the spontaneous emission is that the energy, the exact energy of the electron, you don't know it. You know just that it's roughly equal because you know that the electrons can have a bit higher energy. And of course that this recombination will come after a statistical time that you don't really control. It is a property of the semiconductor. The second emission effect in the photoelectric effect is the stimulated emission. The stimulated emission arises when you have 1 incident photon that comes with an energy h nu, and this photon triggers the recombination. So this recombination occurs only if there is an incident photon. What happens is that the first photon is not transform at all. It will keep on traveling its path. But there will be a new photon that is the exact copy of the initial photon. Okay, so this stimulated emission process is very important because it multiplies the light energy. Okay, a few words about the emission probability. You remember that considering the distribution of energy of the electrons, there will be a distribution of energy that depends on the temperature, but that's not what is very important because usually the temperature is pretty much stable. but we can estimate the distribution of energy, and this distribution of energy here will induce a distribution of wavelength. Okay, so this will be normally you understand that already, but I will say a few words of that after. Last thing, last photoelectric effect, the absorption effect. This one happens when one photon is absorbed by an electron that is in the lower state of energy, which means the valence state. And by this absorption, a new pair of carriers will be created, which means that you will have a hole, so that the white circle in the bottom is a hole, and an electron in the conduction band. Okay. The condition for absorption is just that the energy of the photon has to be higher than the difference between the conduction and the valence band. Okay. So just a few words to summarize here what is important, and especially the link between this distribution of energy and the distribution of wavelength. Maybe I'm going to write it here. So the distribution of energy of the carriers induce the distribution of the emission wavelength. Okay, and we established last year a relationship between this distribution and the wavelength distribution. Where is my equation here? Okay. Okay, the delta E that you have here will induce a delta lambda that can be computed, and that depends mostly on the wavelength. Okay. In particular, you remember that it increases in square of the wavelength, so it means that the higher you go into the wavelength, the bigger, the largest is the spectral width. Okay, and this is problematic because we want to use, let's say, high wavelength lasers, so it's not really a good thing. Okay, so this is the basis that we need to understand to discuss the light source devices. And you remember that the first one that we discussed was the LED. Sorry. So very fastly, I'm going to pass over the LED. You remember that there's one important point here is that we use a PN junction. The PN junction is interesting because on the PN junction, you are going to make carriers of both type, which means electrons on one side and holes on the other side, to recombine on a localized point. Okay, so on the localized surface actually. So this will happen at the junction, and what's as a result, when you put a positive current, you are pushing the electron this way, the carriers the other way, and they meet here at the junction, and that's where you are going to have both spontaneous and stimulated emission in a certain sense. Okay, the structure of the LED is here. Okay, and you remember that the interest of the PN junction in this case that you can put the junction very close to the surface in order to limit the absorption in the semiconductor. Because something that I forgot to say here is that absorption is the most important phenomenon above the tree. The most likely to happen is absorption. So that's something that you want to avoid or compensate by all means. Okay. I'm going to shift that a little bit higher so I can write down. Okay, so I can summarize what I just said on the LED. So the LED is a simple PN junction that localize photon emission at the junction and limits electrical absorption by reducing the thickness of the output layer. Okay, I'm not sure that I'm completely clear. If it's not clear, just let me know. What we need to understand here is that there's big default with the LED when we want to go to high frequencies. First, the emission spectrum is not good because there's nothing that reduces the emission spectrum. So the emission spectrum will be computed by this relationship here, leading to tens of nanometer of spectral width. And the second thing is that the modulation of the power of the LED is limited by the spontaneous emission response time. Okay, so spontaneous emission is the main phenomenon in an LED, the main emission phenomenon. And it is limited by the carrier lifetime. Okay, you remember the carrier lifetime is the time, statistical time at which the electrons will recombine. Okay. The carriers will recombine. And maybe you remember, but last year we did the numerical application of that. And it turns out that in the base case scenario, an LED will be limited to 100 and something, 150 roughly megahertz. Okay. Okay. So it is not possible to discuss what we want to discuss in this course with LED. Okay, we cannot use LED for fast electronic link. Okay, and not only because of the spectral width, but mostly because we cannot modulate the structure faster than that. Okay. So if the LED is not a good candidate, what remains is the laser. Okay, and before I go to this slide here, I need to introduce about the laser. Okay, so okay, remember that, I guess, light emission by stimulated emission of radiation. Basically, it says that the laser is a light source where stimulated emission dominates. I'm going to reduce all that fonts. Okay. In order to achieve that, both populations of carriers must be associated.
Sorry, mister.
Yes.
Yes. Laser is not light amplification by stimulated emission of radiation.
You're right. You're right. Absolutely. Thank you. So both population of carriers and photons must be associated. There's one and unique way to do this okay, specific heterogeneous junction layer 3 is implemented. So it's a very thin layer, okay, thin like that, thin layer, where the refractive index is higher. So this is for the confinement of photons. Okay, we are going to create a waveguide, and where the EG is smaller, so the gap energy is smaller, which and use a confinement. I used to like this word before, but that was in the old world. The confinement of carriers is done by this gap of energy. I'm sorry, I don't have the drawing here, but you probably can find it in your in my documents of last year. Okay, so it's still a PN junction, but with an additive layer that produces a confinement of photons and confinement of carriers. Okay. In addition to this, you will have a cavity. Or maybe I can add that. Also, a cavity made by two mirrors, okay, constrain the photons inside the active layer. Yes, what is important to understand is that everything here is called the active layer. Okay, this heterogeneous layer, a very thin layer called active layer. Okay, it's easy to understand that it is the active layer because that's where stimulated emission occurs and it does not occur elsewhere. Okay. Okay, so this cavity, it induces something that is very important. So you have here the structure of the laser diode, a PN junction, and inside here the red layer, the red band, is the active layer, where you have all the photons and all the carriers, or almost all of them. And on the side, you have the mirrors. Okay, what we discussed last year is that this cavity will also play the role of a selective filter. Okay, you remember there's a phase condition. It gives a free spectral range, so it's not ISL. We are going to change that and remove the lambda, by the way. Yeah, no, I not remove the lambda, but in English, it's free spectral range, not ISL. Same here. I did not validate. Okay, FSR for free spectral range. I'm going to write that a little bit here. This cavity is a selective filter. We call that, by the way, it's a Fabry-Perot cavity. Is a selective filter. Okay. Which this filter, it looks like a comb. A comb is a peigne, un peigne de fréquence. a comb of frequencies or wavelengths that are separated by the free spectral range. As a comb, okay. A comb of frequencies or wavelengths separated by the free spectral range, or FSR. Okay, so that is for the basic principle of the cavity impact inside the laser. To make the laser operate, you remember that there is a gain condition. Okay, so I used to present that. Maybe I think I did not present this like that last year. Basically, the laser can be considered as an oscillator, okay, an electromagnetic oscillator. Any oscillator, any linear oscillator, is made by the same thing, an amplifier and a filter, all in a loop. Okay. If it's going to oscillate, you need to violate the Nyquist criteria of stability. Mark, you asked me something on the forum. What was that? Dirac, deltas, combination? I don't understand. Mark, are you here?
Probably about the comb.
Yeah, probably about the comb. It's okay?
Yes, it's okay. It was only an appointment. That's
okay.
That's all.
Okay. So to make the oscillation, you need to violate the Nyquist criteria. I don't know if you still have some automation courses, but the stability of a system is defined by this criteria. If the evolution of the transfer function in the complex plane goes to the left of the -1, it means that the system is unstable. Here we want the system to be unstable because instability is oscillation. So to have this oscillation, we need to have a gain condition and a phase condition. Phase condition somehow is resumed here by the comb. Okay, the comb fixes the frequencies at which the system could oscillate. The gain condition, it's a different thing. You need to be sure that at these frequencies, you have enough amplification to induce the oscillation. Okay, so maybe I'm going to add some discussion after. So the gain condition. So in order to oscillate, which means in our case to emit a permanent electromagnetic wave in the light domain. Okay, so oscillate here is lasing. The laser needs to comply with a gain condition. This gain condition, we have seen that last year, is that the amplification over a round trip is higher than the losses. Okay, that can be resumed as the total amplification after a light round trip in the cavity. Compensate the sum of losses in the cavity. Okay, so this can be resumed with one equation. I'm going to give you here. This equation here. So this, as I thought, this text is a bit too big. Okay, so we have this equation here, where you remember that R1, R2, actually it's not well spelled, it should be small r. R1, R2. Okay. With R1, R2, the reflection at the cavity mirrors. Okay, so that's the losses because the photons are going out of the cavity. G, the linear gain of the active layer. So it's a gain per meter. Okay. And alpha, do we have alpha somewhere? Yes. Alpha, the linear losses. Okay, so that's electrical absorption mostly. Rate per meter, also per meter. Okay, and L is the length of the cavity. By the way, I'm going to add an index so that we know what we're talking about. LC is the length of the cavity. Okay, so we need a minimum of that to have the laser effect. Okay. Okay. What's important to understand here is that R1, R2, the length of the cavity, and alpha are depending on nothing. Okay, they are basically R1, R2, and alpha. It is the property of the semiconductor, and LC, it's a geometrical length. Okay, so as R1, R2, alpha here, and LC are constant depending only on the semiconductor type. Once the semiconductor is built, okay, the only parameter you can play with is G, and that's the gain. Okay, the only parameter that can be used to achieve this condition is G. That depends on the carrier density and then the injection current. Okay, so from here, from this point, we are going to start discussing about photons and carrier population. Okay, what you need to remember, okay, to be extremely clear, is that you remember maybe the bathtub. What's the name in English? Analogy, the bathtub analogy, which says that the active layer is like a bathtub that you fill with carriers. Well, here you have a population of carriers inside the bathtub, and if you are below the level of Damn, there's a word here. I forgot. Anyway, if you are below the draining level, okay, when you add some carriers, you are just filling the bathtub. You have non-radiative recombination, you have spontaneous emission, but mostly you are just filling this. If you increase the injection, so if you turn on the tap, you will put more water inside, and once you have reached the top of the bathtub, every excedent drop that you put in will be transformed immediately in a drop that will go outside of the bathtub by this, I forgot the name in English. In French would be débordement. Okay, so if you compare that with the what's important, so that's the carrier density and the power out, that is an image of the photon density. Overflow, thanks, the overflow. What you can say is that there is a threshold here, okay, and below this threshold means seuil, below this threshold, if you increase the injection current, the only thing that you increase is the carrier density. And then your carrier density is full or is high enough. And what is going to happen here is that every drop you add will be transformed in photon. And here you will have a linear evolution of the power with the injection current. Okay, the more you put carriers, the more you generate photons, and the more you have optical power. Okay, and this thing is linear until the thermal effects, which I have nothing to add this year. Okay. One thing that is pitiful here is that I say that here it was N0. Actually, it's more accurate to say that it's NTH, which means the carrier density at threshold. So I'm going to change that. NTH. Interesting. Okay. What's wrong with that? Okay, it's a bag. Let's do that second time. Okay, now it works. Yeah, cool. I can just go where it's. Okay, so it's NTH. I have 2 times, 3 times. Okay, so above threshold, the carrier density remains constant at NTH. It does not evolve anymore. Okay. I have a question. Why am I here? Okay, I'm going to discuss the rest after. Apparently, yeah, I skipped some slides, but never mind. Okay, though, yeah. What can I say more here? Yes, maybe I can resume what I just say in the text slide. The notion of threshold in a laser diode. Okay. To overcome or to comply with the gain condition, there is a threshold on the injection current. Okay. I'm going to reduce the font size. Below the threshold, increasing the injection current only impacts the carrier density. No stimulated emission. Above threshold, the lasing condition is satisfied, and probably doesn't stay like that, satisfied, and the each additional carrier is transformed into a photon. What is wrong with here? Additional one. Okay. The carrier density remain constant. Okay. Above threshold, I'm doing like that. So the lasing condition, the carrier density remain constant, and the relationship between injection current and photon density is linear. Okay, I can write here a little bit in advance something that we already know, is that the power out is proportional to, is equal to something called the slope efficiency. So it's eta of the laser diode times I minus I threshold. And this is proportional to S, the photon density. I probably forgot something. Okay, so the power emitted is proportional to I minus ITH, okay, above threshold. And this is proportional to the photon density. Okay, since there's a, we have done one exercise last year to, oh no, are we? Or are we going to do it this year? I don't remember. I guess we did it last year. I'm not completely sure. That links the photon density to the optical power. Okay. One last thing as a reminder to the laser diode is the spectrum emission of the laser diode. The spectrum emission is a combination of the emission probability and the condition of the Fabry-Perot cavity, of the cavity. Okay, so you remember that this combination leads to the emission of several wavelengths. Here I have represented the case where you have two different currents, okay, one I1 and I2, and you see that if you have I2 bigger than I1, then at this current, you are going to have more modes that fit the gain condition. Okay, maybe this slide is not very clear, by the way, but I think I can reduce the image and put some more text to explicitate this. If I can just grab this, perfect. Okay. No, it's a little bit small, but it should be okay. So the emission spectrum of laser diode is a combination of what? The probability recombination. Okay, so this is due to the distribution of energy of the electrons. I remember that is related to this graph here. Okay, in lambda it is the other way around, so that's why you have it here. Okay, like that, and of the frequency condition of the cavity. Some of you have a microphone open. Maybe Mark, it's you from the last question. No, I'm not sure. The frequency condition in the cavity. So generally speaking, it produces a spectrum with several wavelengths of emission that makes the laser multimode, okay, which is not a very good news, which is to avoid for high performances. First, because the modes will interact and reduce the modulation frequency limit. Second, the spectral width is not very good. It's better than with an LED, but it's not satisfying. And it will limit the frequency, the bandwidth, sorry, in the fiber. Because of the spectral, no, the chromatic dispersion. Okay, so I'm going to increase that a little bit and leave some space for the drawing. Okay, so it's not satisfying solution, and in order to avoid that, you may remember that the solution to this is the Bragg reflector. So I'm going to go very fast with that because this has poor impact on the electrical consideration that we will have later, but I have to say a word on that. Remember that the Bragg reflector, it's alternative layer of N1 and N2, so two different layers with refractive index to alternate refractive index, that produces a reflector that is selective. Okay, so maybe I'm just going to write that. The Bragg reflector is a stack of layers with alternate refractive index. Okay, that produces a selective mirror. Okay, the selectivity of the Bragg layer is actually pretty good. It's less than 1 nanometer, and in addition to the Fabry-Perot condition, it will produce a pure monochromatic laser source. Okay, so you remember that there are 3 types of implementation of the Bragg mirrors. The first one is a DFB for distributed feedback. The Bragg is inside the active layer, and you have, which means that you are going to modulate the refractive index inside the active layer. So you have here a microscope, electronic microscope photography of one DFB before the top layer is implemented. Okay, so this will produce an almost purely monochromatic laser source. The second implementation is when you put the Bragg layers outside on both sides of the cavity, replacing the usual mirrors. Why is it interesting is because now the mirrors are not implicated into the production of photons. So it's interesting because we say it's a multi-section laser source, which means that you can change the materials here. Like for example, in this photo, you see a mirror made of alternative layer of air and semiconductor. So you can play with very more contrasted indexes and reduce the number of layers, for example. I also discussed with you last year of the possibility to tune the frequency, the selective frequency, by playing with current inside these mirrors. Okay, but here we are not going to discuss that too much. And eventually, the last implementation is on the vertical side. And you remember I told you that this solution is interesting because it's very cost efficient. You are going to make layers on the same plane as the PN junction. And this is interesting for money-wise because you see you are going to produce a very high density of laser source. With very short size, small sizes. So the more you produce on the same surface, the cheaper the electronic component. The difficulty here, and we are going to discuss about that later, is that the electrical path for the electrons goes at the minimum through one of the Bragg reflectors, and this induces some difficulties, some electrical difficulties in that kind of laser sources. Okay. I think that's enough for today, unless you have questions. And I'm open to any question, and I repeat that you can ask question in French.
Can you explain a little bit about the images that we have here? What is here down? I don't understand.
Down? Okay, yes,
yeah,
I can say a bit more. The point, okay, if we consider this type of laser diode, the light goes out on the side, okay, on the edge. So they are called edge emitters. So this one, but also this one, okay, they are edge emitters. If you want to have the laser effect, you need to cut the semiconductor structure to let the light out of the device. Here with the VCSEL, the light goes from the top. So it means that you can use that kind of laser as matrices. Okay, so you have a full board of components and they all can produce light, okay, from the top. So the use as a matrix is interesting because first you can produce a very intense light. So you can emit a lot of power, but you can also imagine a communication system with several outputs, several paths. If, for example, they have a slightly different wavelength, and you are capable to, on the same fiber, to eliminate, to separate, sorry, the different wavelengths. Also, the step between two of these lasers are high enough so that you can present several fiber to it, and you can have very compact multiplex system with several fibers. Okay, so these are all photographies of the top view of this kind of laser source.
Okay, thank you. Interesting.
Do we have more questions about that or about something else?
So will you put the slides on Moodle, the updated ones?
Yes, absolutely.
All right.
I will, as well as the link of the video.
Perfect.
Excuse me, do you have some bibliography that we can check to review the material covered today?
Yes, I'm going to add that as the information on Moodle too.
Okay, thanks.
Yes. I have at least 2 or 3 books in English that discuss that. Be careful, because these books usually are at a higher level than what I present to you. They are more like research books, but I think if you are really interested, it's okay to follow that. Okay, it does not exist even in English language. A book that is addressing this issue at the level I am addressing it. It's either too low, either a bit too high.
Okay, yeah, it doesn't matter if the books are in French. I can understand that.
In French, it's even worse. There are more literature in English, but they are not. Well, the book that I will list is a bit. It's more for researcher than for students.
Okay, but it covers the diodes.
But it covers absolutely
everything we saw today.
Yes. And what we are going to see in the next days.
Okay. Thank you.
If there's no other question, I'm going to wish you a good afternoon. Yes?
Yeah, there is a test of 2013 on Moodle.
Yes.
It's we can try to do the exercise as well as now, or
oh no, you have to wait for at least a few classes.
Okay.
But I'm going to check about it, because 2013 seems a bit old to me.
All right.
Maybe I'm going to update that.
All right, perfect. And could you say during the lesson if one of the exercises can be done
yes.
by ourselves?
I will definitively do that.
All right, perfect. Thank you.
And by the way, how are you going to grade this class?
There will be an exam.
It's just an exam?
Yes, it's just an exam.
Okay, thanks.
No worries. No other questions? Guys, have a good afternoon. Bye.
Thanks so much. Bye.
Bye. Thanks.
Bye. Thank you.
Bye.
Bye.
Bye.